The massive 468-foot steel cargo hull was not a tanker, but a C-3 freighter carrying the heavy fuel needed to move itself across the open ocean. Yet this robust architecture encountered a severe mechanical contradiction when the vessel suffered structural compromise, losing its buoyancy and sinking to the seafloor in barely 30 minutes, permanently trapping its hazardous payload in the cold abyss. What remained completely unknown in the immediate aftermath was exactly how much of that heavy residual fuel survived the initial violent descent, and precisely how long the deteriorating steel framework could continue to contain it under the immense crush of the sea. The mechanism of the loss fundamentally dictated the conditions of the eventual salvage, locking the vessel and its cargo in a state of suspended physical decay that would not be challenged for nearly half a century. The ship was originally built as a standard C-3 cargo carrier, a workhorse of mid-century maritime logistics designed for heavy payloads and long transits. By the summer of 1953, the vessel was loaded with railroad, automotive, and other war materials bound for South Korea, but its most consequential hidden load was its own operational fuel. The ship carried an original bunker fuel capacity of 457,000 gallons of heavy residual fuel oil distributed throughout multiple deep tanks and lower hull spaces. This specific grade of fuel was thick, heavy, and extremely difficult to move even under normal operating conditions, requiring internal heating coils simply to flow through the ship engine room piping. The deep tanks were integrated directly into the lower structural framing of the hull, meaning the fuel containment relied on the primary structural integrity of the ship itself. The operational boundary of the vessel collapsed suddenly in dense fog outside the Golden Gate, when a sister ship struck the starboard quarter of the cargo carrier. The collision tore into the starboard quarter and caused massive structural damage, opening the ship to a flooding casualty that moved faster than the crew could reverse. With the heavy cargo still aboard and the ship losing buoyancy, the priority shifted from prolonged damage control to survival and evacuation. The stern settled as the casualty accelerated toward an unrecoverable sinking. Within 30 minutes of the collision, the vessel slipped completely beneath the surface, beginning a rapid descent through the water column. During that descent, the hull carried the unresolved damage of the collision rather than a neatly sealed industrial load. On the bottom, the wreck came to rest on its side in roughly 180 feet of water, with part of the hull buried below the seabed and oil-bearing spaces still hidden inside a torn, obscured structure. Later surveys would find some hull plating near the fuel tanks in better condition than expected, while tank piping, vent lines, and sounding systems had deteriorated severely. The sinking converted the casualty into a submerged containment problem beyond immediate technical reach. A massive environmental casualty sequence eventually began to unfold along the coast, but it did not begin as a clean, one-time mystery. Since at least the 1970s, recurring winter oiling events had appeared across central California, often after major storms, leaving oiled seabirds and tarballs without an obvious active casualty on the surface. The winter of 2001 to 2002 made the pattern impossible to ignore. Investigators could not tie the oil to a current vessel source or an active surface casualty, so the search shifted away from ordinary patrol assumptions and toward a recurring, stationary, man-made source hidden below the waterline. That pattern accelerated the deployment of advanced trace evidence analysis. The analysis had to test whether a weathered historical fuel could be separated from seeps, other wrecks, and modern discharges. Heavy bunker fuel does not simply dissolve in the ocean, it weathers, shedding its lighter volatile components over time while retaining its dense, complex hydrocarbon core. To trace the origin of the spills, scientists used oil chemistry and fingerprinting, comparing tarballs, bird samples, and source samples against a petroleum reference library. Laboratory analysis separated and measured hydrocarbon patterns and biomarker ratios, building a chemical profile detailed enough to distinguish bunker fuel from natural seeps, other wrecks, and unrelated vessel discharges. The result was not a perfect biography of every additive in the fuel, but a defensible forensic match between the mystery oil and a specific old maritime fuel source. Those matches pointed to an old maritime bunker fuel source, and the wider investigation then moved from chemistry to location. By combining those chemical matches with beach sampling, wildlife stranding patterns, satellite and lidar searches, wreck databases, and direct samples collected above the site, the investigative team narrowed the source to a specific wreck sector west-southwest of the Golden Gate Bridge. The search converged on the SS Jacob Luckenbach, resting roughly 17 miles from the bridge, and on the bunker fuel known to have been aboard when the cargo hull sank in 1953. The identification linking the trace evidence to the wreck transformed the situation from a generalized environmental mystery into a targeted engineering imperative. The forensic evidence showed that the old cargo hull was a chronic source, with oil escaping through cracks, vents, compromised pathways, and deteriorated piping rather than through a single, newly discovered rupture. That identification set the next task: turn a chemical match into a physical recovery plan. The fingerprint could identify the leaking source, but it could not tell engineers where the oil remained or how the structure would respond to access. The investigation now had to bridge the gap between microscopic chemical proof and heavy physical access, forcing engineers to figure out how to safely interact with a massive, deteriorating structure suspended in the darkness. Acoustic and optical sensors mapped the exterior steel shape, but marine growth, poor visibility, uncertain orientation, cold bottom water, and strong reversing currents made every access decision provisional. ROV teams could descend and document the hull, yet the site's conditions narrowed working windows and made tether management around jagged wreckage a constant risk. The specific depth constraint fundamentally altered the scope of the mission. The hull rested in roughly 175 to 180 feet of water, in bottom temperatures reported around 4 to 8 degrees Celsius. The ROVs navigated through the gloom using sonar and cameras to build a digital picture of the wreck, revealing its list and the extensive damage from the historical collision. Those conditions made the survey reliable at the level of overall form, but not at the level of fittings, tank access, or recoverable oil. The digital resurrection of the shipwreck provided vital macro-scale data, but it could not answer every micro-scale engineering question required for a safe intervention. Surveys showed a complicated wreck. Parts of the hull plating near the fuel tanks were better than expected, while vent, sounding, and tank piping systems were badly degraded. ROVs could help watch, map, and document the site, but they could not perform the sustained tactile work needed to clear growth, position equipment, verify fittings, and adapt the plan when the wreck refused to match the drawings. This set the operational threshold. Remote survey could define geometry but not mechanical access. The unresolved questions were now practical. Which fittings could be cleared, seated, and loaded without opening new failure paths? The command had to accept that controlled recovery would require commercial divers to work directly at the hull, attach engineered interfaces, and make cautious decisions on site under ambient seawater pressure. Those requirements made saturation diving the working platform rather than a purely conventional surface diving schedule. At roughly 165 to 180 feet of working depth, matching the same daily bottom time with surface-supplied methods would have demanded many dives and roughly 50 hours of decompression time across the operation cycle. The solution was a full saturation diving spread supported by additional surface-supplied dives during assessment and recovery. The divers lived inside a pressurized deck habitat, commuted in a pressurized diving bell, and worked in hot water suits for repeated bottom periods while the barge, ROV teams, and topside engineers supported the oil recovery system. The access problem was not a dramatic blowout from a pressurized tank, but controlled entry into oil-bearing spaces surrounded by ambient seawater pressure, deteriorated fittings, and thick fuel that could leak if disturbed. The teams used hot tap assemblies and sealed valve and flange interfaces to create controlled access points while minimizing release risk. Before each connection was used, divers cleared enough marine growth to seat the equipment, checked the fitting, and allowed the recovery system to take the load rather than relying on the old hull alone. Once an access point was established, drilling, valving, pumping, and monitoring followed professional salvage procedures built around containment. Each tap became a pathway that could be pumped, isolated, and later capped or blanked. The saturation divers repeated the sequence across multiple access points, building secure valves along the wreck's exterior. The 28-day saturation runs gave them the pace needed to test each plate and confirm that fragile 50-year-old bulkheads could tolerate the applied stress. Access was now controlled, but recovery still depended on making the fuel itself move. Standard fluid suction protocols immediately struggled when applied to the wreck because the cold ocean and the fuel chemistry turned much of the bunker sea into a waxy semi-plastic mass. The controlling variable was no longer only volume but flow. At bottom temperatures in the 4 to 8 degrees Celsius range, some oil was reported as tar-like, with viscosity above 300,000 centistokes. Other pockets were less viscous, but the overall product was too thick and inconsistent for ordinary salvage pumping. The heavy fuel could not simply be pulled through narrow access points and lifted to the surface without heating, circulation, and a specialized pumping system. To overcome this material behavior, the engineering command deployed a specialized viscous oil pumping system designed to change the thermal behavior of the fuel before extraction. Divers and topside crews installed heat exchangers and in larger tanks, supplemental live steam injection nozzles. Steam lances were also used for local heating near the pump. The goal was not to heat every tank uniformly to 170 degrees. Instead, the operation heated and circulated the oil for hours or days until average tank temperatures reached the pumpable range, with reports of about 105 to 130 degrees Fahrenheit, before pumping and higher temperatures only near the heat exchangers. As the fuel warmed, viscosity dropped enough for the recovery system to move it. Heating made the oil pumpable, but movement out of the wreck introduced a second constraint. Heat loss through hoses, tank walls, and seawater could cool the suction side, clog the line, or drive discharge pressure beyond practical limits. The solution used the viscous oil pumping system with annular water injection, or AWI. A small flow of warmed water was injected into the suction or discharge path, so that water coated the inside of the hose and reduced oil-to-wall friction. It was not a frictionless pipe, and it was not simply insulation. It was a moving, lubricating layer combined with heating and circulation that lowered pressure drop, helped keep the pump inlet warm, and allowed the heavy fuel to reach the recovery barge in a controlled stream. The extraction process eventually reached a hard engineering stop. Beyond a certain point, recovering more oil meant disturbing areas that were smaller, more scattered, or unsafe to reach. Over weeks of operation, the viscous oil pumping system recovered about 85,000 gallons of heavy bunker fuel and transferred it safely to the surface. That figure defined the documented recovery result, while later assessments treated the remaining oil as an estimate rather than a measurable inventory, with roughly 29,000 gallons believed to remain in small overhead spaces and other inaccessible locations. The missing volume had not vanished into a single clean reservoir. When the ship first sank, warm bunker fuel escaped or migrated through hull cracks, vents, and compromised bulkheads. What stayed aboard became trapped in cargo space overheads, between decks and among frames. By the time salvage crews reached it, the problem was no longer a central tank inventory, but scattered pockets and structural traps, some unreachable from the side, most accessible to divers. The final trapped gallons were concentrated behind cargo, in overhead pockets, and in starboard side spaces that could not be reached without massive tunneling or other intrusive work. Each additional cut or excavation would have increased diver exposure, disturbed unstable debris, and risked new leakage paths for a diminishing return, so the site's physical limits became the management boundary. Salvage success was defined by accessible removal, secure closure, and continued risk control. That recovery volume marked the practical limit without pushing risk beyond the benefit. Residual oil still required monitoring because major storm events could still rock the structure hard enough to release small amounts in later years.